if we divide the mass of the substance given in grams with the relative mass of the particles it is composed of, expressed in grams, then we get the number of moles. And if we divide the same with the molar mass of the particles, then we get a physical quantity called amount of substance. And number of moles and amount of substance are pretty much the same. The difference being number of moles is unitless, whereas amount of substance has the unit mole. Amount of substance is a physical quantity in the SI system. And you know that 1 mole of any substance contains an Avogadro's number of particles. Avogadro's number is denoted by capital N or capital N with the subscript 0. And we can think of number of moles as number of dozens. See, by definition, 1 dozen is 12 items. So if I have 1 dozen apples with me, I have 12 apples with me. And if I say I have 2 dozen apples with me, then how many apples do I have? If 1 dozen means 12, 2 dozens would mean 2 times 12, right? So I have 24 apples with me, as simple as that. So if 1 mole of any substance contains an Avogadro's number of particles, then n moles of that substance would contain how many? Simple. You have to multiply the number of moles with Avogadro's number, right? So to get the number of particles present in any substance, given the mass of the substance, first figure out the number of moles, then multiply the number of moles with Avogadro's number to get the number of particles. Same in this flow also. If you divide the mass with molar mass, you would get amount of substance in moles. And 1 mole of any substance contains an Avogadro's constant of particles. Avogadro's constant is denoted by capital N with the subscript A or the letter capital L. So to get the number of particles given the mass, you can first figure out the amount of substance by dividing the given mass in grams with its molar mass, and you will get amount of substance in moles. And if you multiply that with Avogadro's constant that has the unit per mole, the units get cancelled and finally you would get a dimensionless number for the number of particles. These two are one and the same. Here we are multiplying it with a dimensionless Avogadro's number. Here we are multiplying the amount of substance with Avogadro's constant that has the unit per mole, so that these units get cancelled. So these two are pretty much one and the same. Let us work out a few examples end to end. That is, given the mass of the substance, we have to calculate the number of particles. Here is a purple colored salt called potassium osmate, and this is its formula, and we are asked to calculate the number of formula units in so much of this salt. And we are given the atomic weights of all the elements present in this compound. How do we do this? How do we figure out the number of particles given the mass of the substance? It is a two-step process, right? First you have to figure out the number of moles or the amount of substance. Then you have to multiply the number of moles with Avogadro's number, or if you have amount of substance, you have to multiply it with Avogadro's constant. Both mean the same. You would get the same answer. But how do we get the number of moles in the first place? To get the number of moles, we have to divide the mass given in grams with the relative mass of the formula unit expressed in grams. Now the mass given in grams is 9.2, But how do you get the relative mass of this formula unit? You know how to do that. This is the formula and here are the atomic weights. And upon calculation, you would get the relative mass of this formula unit to be 368.0. And if you express that in grams, it would be 368.0 grams. So this is the number of moles. Then how do you get the number of formula units? You have to multiply the number of moles with Avogadro's number, capital N or capital N with the subscript 0. So that would be 9.0 grams over 368.0 grams multiplied with 6.022 into 10 to the power of 23. I will leave the simplification to you. Remember, for the sake of figuring out the number of significant figures, take this value of Avogadro's number as an exact value. So that means assume that this has an infinite number of significant figures. We know the value of Avogadro's number exactly as of today. Now if you want to answer this question using the physical quantity amount of substance denoted by small n, you can do that. For that, you have to divide the mass given with the molar mass of this substance expressed in gram per mole, and it becomes 9.2 grams over 368.0 gram per mole. So these units get cancelled. Then if you want to get the number of formula units, you have to multiply the amount of substance with Avogadro's constant n with the subscript a. So then it becomes 9.2 over 368.0. This mole inverse goes into the numerator, becomes mole, multiplied with Avogadro's constant is 6.022 into 10 to the power of 23 per mole. Now these two units get cancelled and you will get the same expression for the number of formula units. Two different ways of solving the same problem. Here we are using the physical quantity amount of substance, here the number of moles. And the next question says, which of the following substances has more constituent particles? Here we are given the masses of 4 different substances. And hydrogen chloride is a covalent compound and it is composed of HCl molecules and its molecular weight is 36.5. 1 plus 35.5 is 36.5. So that is its relative molecular mass. To get the number of molecules of hydrogen chloride, first you have to figure out the number of moles. For that you have to divide the given mass with the relative mass of hydrogen chloride molecule expressed in grams. So this is the number of moles. Then you have to multiply it with Avogadro's number to get the number of hydrogen chloride molecules, and Avogadro's number is approximately 6.022 into 10 to the power of 23. And for our calculation, assume that this is the exact value of Avogadro's number. That means it has an infinite number of significant figures. And I let you do the simplification. Then what about 56 grams of iron? Let us figure out the number of iron atoms using the physical quantity amount of substance. You know the relative atomic mass of iron is 56, that is its atomic weight. Then its molar mass would be 56.0 gram per mole. Then how do you get amount of substance of iron? You have to divide the given mass, that is 56.0 grams, with its molar mass, that is 56.0 gram per mole. And to get the number of iron atoms, you have to multiply the amount of substance with Avogadro's constant. So it would be 56.0, cancel these two, take mole inverse into the numerator. So it would be 56.0 over 56.0 mole multiplied with Avogadro's constant is 6.022 into 10 to the power of 23 per mole. Don't forget that. So cancel these two and simplify it. I will let you do the math for the remaining two, and to answer this question, compare all these four values. I think you can do that. Now this question is a bit interesting. In each case, the mass given is the same and we are asked to find out the number of oxygen atoms. See, all these three are ultimately made up of oxygen atoms and nothing else. In nascent oxygen, you have only independent oxygen atoms. There are no molecules. By oxygen, we mean oxygen that is composed of oxygen molecules. And each oxygen molecule is a group of two oxygen atoms. And ozone is O3, and each ozone molecule is a group of three oxygen atoms. So, they're all ultimately composed of oxygen atoms, but the difference being how they are grouped. Therefore, if they all have the same mass, then they must all have the same number of oxygen atoms ultimately, right? So, here you don't have to do three separate calculations. If you figure out the number of oxygen atoms in 16 grams of nascent oxygen, then 16 grams of oxygen that is composed of oxygen molecules, 16 grams of ozone composed of ozone molecules would all have the same number of oxygen atoms ultimately. I hope you understood the reasoning behind this. Because the number of oxygen atoms are the same, because the mass of oxygen is the same and all these substances are composed of only oxygen atoms. The difference being the way they are grouped. There is no grouping in case of nascent oxygen, but in case of oxygen, you will find groups of two oxygen atoms each. And in case of ozone, you will find groups of three oxygen atoms each. Therefore, these three cases would have the same number of oxygen atoms. So it is sufficient if you find out the number of oxygen atoms in the first case. Then how do you find out the number of oxygen atoms in the first case? You have to divide the given mass in grams with the relative mass of the particle expressed in grams. Here, in case of nascent oxygen, the particle we are talking about is oxygen atom. And the relative atomic mass of oxygen is 16.0. When expressed in grams would be 16.0 grams. And these are the number of moles of oxygen atoms. To get the number of oxygen atoms, you have to multiply it with Avogadro's number. And the remaining two cases would also have the same number of oxygen atoms. If you want, you can do the math for yourself and figure that out. And we can add one more case here. Let us say a sample of a metal oxide upon analysis was found to contain 16.0 grams of oxygen in it. Then how many oxygen atoms are present in this sample of metal oxide? Same as this. It doesn't matter in what form that element is present in. If the mass is same, the number of atoms must be the same. So, a given mass of an element will always contain the same number of atoms irrespective of the form in which it is present, whether it is in elemental form or whether it is in the form of a compound, whether it is in the form of atoms, molecules, Doesn't matter, right? And the next question is also highlighting the same point. A metal carbonate upon analysis was found to contain so much of carbon. Then how many carbon atoms are there in this sample? It doesn't matter in what form this carbon is present in. A given mass of carbon always contains the same number of carbon atoms. How do you get the number of carbon atoms? Given mass in grams over its relative mass expressed in grams multiplied with Avogadro's number. I will let you do the simplification. In the next question, we are asked to express the mass of a mosquito in unified atomic mass units. And I think we can do that. But remember, unified atomic mass unit is incorrectly referred to as one atomic mass unit in many textbooks. So you have to learn to do this mistake for the sake of your tests. 1 U is not actually equal to 1 AMU. They are two different units of mass, but many textbooks use them synonymously. We have to live with it. So understand that 1 U is 1 AMU as far as your tests are concerned, but they are not actually equal. Now, how can you express the mass of this mosquito in unified atomic mass units? You know 1 U is equal to 1.66 times 10 to the power of minus 27 kilograms. And if you flip it, that means 1.66 into 10 to the power of minus 27 kilograms means 1 U. Then how much mass do we have? This mosquito weighs 2.5 milligrams. That means 2.5 into 10 to the power of minus 3 grams, or multiplied with 10 to the power of minus 3 again kilograms. So it would be 2.5 into 10 to the power of minus 6 kilograms. That is the mass of this mosquito in kilograms. So if these many kilograms mean 1 U, then 2.5 into 10 to the power of minus 6 kilograms means how many U? So the mass of the mosquito in U is equal to 2.5 into 10 to the power of minus 6 kilogram times 1 U over 1.66 into 10 to the power of minus 27 kilograms. So cancel these two and simplify the answer to get its mass in U. Remember, unified atomic mass unit is a unit of mass, just like kilogram is a unit of mass. But kilogram is an SI unit of mass, whereas U is a non-SI unit of mass. This question says, if all the oxygen in potassium chlorate can be liberated upon heating, calculate the total number of oxygen molecules that can be produced from so much of potassium chlorate. Obviously, to figure out the number of oxygen molecules produced, you must know the mass of oxygen gas produced from this sample. Because all the oxygen present in this sample gets liberated upon heating, the mass of oxygen gas produced from this sample must be equal to mass of oxygen present in this sample of potassium chlorate. So if you can figure this out, you would know this. How do we figure this out? See, potassium chlorate is an ionic compound and this is its formula. From this formula, we understand that in one formula unit of this compound, there are 3 oxygen atoms. That is obvious, right? But if you take 1 mole of this compound or 1 mole of potassium chlorate, then how many moles of oxygen atoms are there in it? Obviously 3 moles, right? It is just like multiplying both sides or both of these with 1 mole. Then what is the mass of 1 mole of potassium chlorate? It is simply its relative formula mass in grams. You know its formula and you know their atomic weights. And upon calculation, you will find its relative formula mass is 122.5. So 1 mole of potassium chlorate means 122.5 grams of potassium chlorate. So if you took 122.5 grams of potassium chlorate, then you would have gotten 3 moles of oxygen atoms. By the way, what is the mass of 1 mole of oxygen atoms? Pay attention to this. Because we are talking about 1 mole of oxygen atoms, oxygen composed of oxygen atoms, it is its relative atomic mass in grams, and relative atomic mass of oxygen is approximately 16.0. It would be 16.0 grams. So that means 3 times 16.0 grams of oxygen. So if you had taken this much of potassium chlorate, you would have gotten this much of oxygen, but you took 6.25 grams of it. So 6.25 grams of potassium chlorate would produce how much oxygen? So the mass of O2 produced is equal to 6.25 grams multiplied with 3 times 16.0 grams over 122.5 grams. So you do the simplification. So you got the mass of oxygen produced. So that is 6.25 times 3 times 16.0 is 48.0 grams over 122.5. This is the mass of oxygen. Then how do you get the number of moles of oxygen? You have to divide the mass given with the relative mass of the particle expressed in grams. Here we are talking about oxygen molecules, so the relative mass of the particle is 32. When expressed in grams would be 32 grams, so these two get cancelled. So this would be the number of moles. Then the number of molecules would be, number of moles is denoted by small n. You have to multiply the number of moles with Avogadro's number. So that would be this whole thing multiplied with 6.022 times 10 to the power of 23. Now what do we have here? 1 gram atom of an element means 1 gram of that element. True or false? Obviously false. 1 gram atom of an element is its atomic weight or relative atomic mass expressed in grams. It is not 1 gram of that element. Which of the following contains the same number of atoms as 20 grams of calcium? Atomic weights are given, the masses are also given, so I will let you figure this out. An atom of an element was found to be 2.02 times as heavy as an atom of C12 isotope. What is the atomic mass of that element? Simple. What is the atomic mass of C12 atom? By definition, it is exactly 12 U, or incorrectly called AMU. So then the atomic mass of some other atom, that is this atom, that is 2.02 times as heavier, this would be 2.02 times 12.0 U. That's it, or AMU. No big deal. What is the combined mass of 1 gram atom of sodium and 1 gram atom of aluminum? Simply 23.0 grams plus 27.0 grams. Is it 50 grams? What is the mass of one atom of sodium in kilograms? What is its atomic mass? Approximately 23.0 U, right? So it would be 23.0 times, you know, 1 U is equal to 1.66 times 10 to the power of minus 27 kilograms, or sometimes referred to as 1 AMU. So it is 1.66 times 10 to the power of minus 27 kilograms. That's the answer. You simplify it. How many kilomoles of methane are present in 16 kilograms of methane? Kilomoles, right? One way to solve this problem is first find out the number of moles. For that you have to convert the given mass into grams. It is given in kilograms. Then divide it with the relative mass of the particle that we are talking about. Here we are talking about methane. It's a compound. It is composed of methane molecules, and the relative molecular mass of methane is 16. 12 plus 4 times 1.0 is 16.0. So relative molecular mass of methane expressed in grams is this much. Then to get the number of kilomoles, you have to divide the number of, or simply you have to multiply the number of moles with 10 to the power of minus 3. That is 16 times 10 to the power of minus 3 grams. 16 times 10 to the power of 3 grams over 16.0 grams times 10 to the power of minus 3. These two get cancelled, and you do the simplification. So that is how you can figure out the number of kilomoles. Or you can directly get the number of kilomoles by dividing the mass given in kilograms with the relative molecular mass expressed in kilograms, right? So it would be 16 kilograms, and the relative molecular mass of methane is 16.0 kilograms. As simple as that. You would get the same answer either way.